Our next speaker is Svjetlana Terzić from University of Montenegro. She will tell us about Grassmann manifolds and modular spaces of weighted and pointed stable genus zero curves.
Yes, thank you very much. So I'm extremely glad to talk on this occasion dedicated to Victor Buchstaber, since I have collaborated with him a lot, and I have had from this a great influence, and I'm happy about that, and I hope it will be continued. So I'm going to speak as well about some present you some our joint results. Actually, I'm going to present one connection we established between our study of the torus section, compact torus section on the Grassmann manifolds and the moduli spaces of weighted and pointed stable genus zero curves. For the facts and the results, I'm going to use on the compact torus section on a Grassmann manifolds. I'm going almost to use these three references, our actually relatively recent papers, and for the results on the moduli spaces of weighted curves, I'm going to refer to the paper by Brendan Hassett, where actually these notions were introduced. And just as a small introduction to provide you with a rough picture about what I'm going to talk about. In our paper, which I referenced above, we constructed the model for the orbit space Gn2 by Tn. I'm going to speak about later about it in more detail, but just to overview. And our model is just some topological space Un, which is the product of the hypersimplex delta n2 and some smooth compact manifold, and a continuous projection from this space Un to the orbit space of the Grassmann manifold. Delta n2 is a hypersimplex. It's not manifold with corners. It's a manifold in modern terminology in general with generalized corners. So UN is a manifold with generalized corners. And in order to define this projection G, we needed to develop some additional structure on these objects we use. Additional structure on the hypersimplex delta n2, on this smooth manifold Fn we introduced, and on Grassmann manifold Gn2 itself. This additional structure consists of stratification of this Grassmann manifold Gn2, which is invariant under algebraic torus action, because the action of the compact torus of Grassmann manifolds, it extends to the algebraic torus action. Then the orbit spaces of these strata by the action of the algebraic torus. Then the corresponding subspaces, we assign to each stratum the corresponding subspace in this space Fn. And we also need to have some chamber decomposition of the hypersimplex delta n2, which is going to again correspond this stratification and some spaces of parameters over chambers. These are some notions we had to develop in order to construct our model for this orbit space, and I'm going to say about it in more details. And then, as I said, when we described this stratification, we assigned to each stratum some space of parameters, and so which is the orbit space by the action of the algebraic torus, and some virtual space of parameters, which is actually subspace of this smooth compact manifold Fn we introduced. And we set point on the orbit space of the Grassmann to be singular if these spaces are not homeomorphic. And we actually proved that our model resolved the singular points on the Grassmann manifold Gn2. On this orbit space. What does it mean? It means that we proved that if we remove these singular points from the orbit space of the Grassmann manifolds, we obtain an open dense set. It's pre-imaged by our projection G we constructed is open dense set in UN, and we proved that our map outside these points is a diffeomorphism. So this is very rough picture. I'm going to say about it in more details. On the other hand, we have a very well notion, I just going to recall very well known facts. We have moduli spaces, smooth are reducible complex projective curves of genus 0 with then marked numbered pairwise distinct points. For example, for G equal to 0, this moduli space is a point because every curve C is a CP1 and any true distinct points can be transformed to 0, 1, infinity. For when genus is equal to 0 and n is equal 4, this moduli space can be identified with the CP1. C can be identified with CP1, x1, x2, x3 with 3 points 0, 1, infinity, and we are left with the point T, which cannot be 0, 1, infinity. So the moduli space is MO4 is CP1 without these 3 points. Generally speaking, when we have a genus curves of genus 0 with the n fixed points, distinct fixed pairwise numbered points, then this moduli space can be identified with these with CP1, 0, 1, infinity, T1, Tn minus 3. So actually, this moduli space is given by this subspace is CP1 n minus 3, where each of the coordinate is no 0, 1, infinity, and coordinates are different. And it is well known that MGN can be given orbifold structure. The structure is not smooth when the genus is greater or equal to, and the MGN is a not compact manifold where n is bigger or equal 4. And now here in the literature, one can meet the problem very often and famous problem of a good compactification of this space. What does it mean, a good compactification? So compactification should be itself a moduli space, which parameterizes some natural generalization of the objects for the space MGN. And in that context, it's widely known the Yin-manifold compactification, MGN bar, of this space MGN. This is compactification by the moduli space of rational stable n-pointed curves. Curve C, where S are the points of genus G. What are these? I mean, just overview, what are these curves? These are curves, rational stable, these stable n-pointed curves. The only singularities on these curves are nodes. Marked points are distinct and non-singular, and they are, for any curve, there are finitely many automorphisms of this curve.
Why rational? Here, consider curves that are genus.
Here I'm going to restrict myself to 0, so that's I speak rational, but in general no. And equivalent condition for 3 in a language algebraic geometry that the stable curves that there are finitely many automorphisms for each such curve is that equivalent condition for 3 is that this divisor is an ample divisor where Kc is a canonical class of C. And for G equal to 0, this the Yin-manifold compactification coincides with the Grothendieck-Coulomb compactification and from the different approaches, and it is known to be a smooth manifolds. And one can, I mean, in terms of algebraic geometry, in terms of stacks, one can find a literature formulation that M bar Gn is smooth connected proper over Z, the Yin-manifold stack. And say, for example, M04 compactification, which is CP1 minus 3 points, is just CP1. And then why I was talking about this, then Brendan Hassett in his paper, he actually enriched this theory by introducing the notion of weighted stability. He considered generalization of these stable n-pointed curves, and he assigned to the mark points, he assigned the data. The weighted data on a set S is a function from S to rational numbers. So to each point he assigned a weight which is between 0, bigger than 0 and less equal 1. And he defined the curve to be A-weighted, stable, if it is satisfied. So it's a generalization of third condition that this Kc plus some AI Si is an ample divisor. So now any point Si is multiplied by its weight Ai. And in this case, also curve has to have singularities of no type singularities, but these points, these marked points, do not have to be distinct in general. So it has a second condition for each subset E of S. If Si pairwise coincide for I is S, it holds that the sum of the weights is less equal to 1. These are his condition of weighted stable pointed curves. And now this condition that this divisor is ample implies that 2j minus 2 plus sum of the, so the degree of the divisor has to be positive, so this sum has to be non-negative. And then we see that the usual stability condition corresponds to the case when the all weights are equal to 1. And then he considered by M bar GA the modular space of A-weighted stable curves. And his main result, published in this paper, he actually proved the analog result of that by Deligne-Mumford. He actually proved that this is a smooth connected proper set proper over Z Deligne-Mumford tract. And besides that, he constructed the reduction and forgetting morphisms between these spaces under some additional conditions the weights should satisfy. I mean, forgetting a reduction morphism, which already actually he generalized this notion, which already existed in theory of Deligne-Mumford theory. And so this is as I said, one hand we have our model for the orbit space of the Grassmann manifold, and the other hand we have this theory of Brendan-Hassett, which was developed later, much developed, on the weighted stable n-pointed curves. And I'm going to present you how we established a relation between these two categories. One topological category, our category is purely topological. Purely described in terms of topological terms, and this is the theory in terms of purely algebraic geometry. We introduced, using the results of Brendan-Hassett, we introduced the notion of Hassett category, H0n. Actually, we considered only weighted curves of genus 0. So the objects in our disk, we call it Hassett category, are the spaces M bar 0A, so of the stable A-weighted curves of genus 0, where the weights satisfy the conditions when we put G equal to 0, given by Hassett. And the morphisms are those described by Hassett, so forgetting and reduction morphisms. And the main result I'm going to describe here is that our model for the resolution of singularities of the orbit space provides topological model for the Hassett category. And in the rest part of our talk, I'm going to explain how we establish this connection. So now about our work on a compact torus action on Grassmann manifolds. So we consider GN2 complex Grassmann manifolds, so two-dimensional complex subspace in Cn. We consider compact torus. It acts on Cn by the coordinates wise action. This action induces the canonical action of the torus Tn of the Grassmann manifold GN2. It's any two-dimensional subspace. It maps to two-dimensional subspace. And I mean, we know that this action of the compact torus extends to the action of the algebraic torus, C star n. And then when we consider Grassmann manifold GN2, we have, I mean, in general, for any complex Grassmann manifold, we have a Pluker coordinates. Pluker coordinates, we take an element L from the Grassmann manifolds, write it down matrix time vertex of dimension n times 2, and all 2 times 2 minor give the Pluker coordinates embedding in some complex projective space of the corresponding dimension. And then using Pluker coordinates, it is a classical standard, say, one can find in any book, standard moment map, which maps the Grassmann manifold to Rn in the following way. It's just a convex span of the vectors lambda I, Zn, where lambda I is n vectors which have lambda I is an n vector which has at two places 1 indexed by I, and in the other n minus 2 places it has 0. I is two element subsets from 1 to n, and then we form this vector lambda I for each two element subset I from 1 to n. And then using Pluker coordinates, we form convex, it has to be norm here. We form a convex combination of this vector lambda I. This map mu is Tn invariant, where Rn considered is with trivial Tn action. And the image of this mu is the hypersimplex delta n2. It's a convex polytope whose vertices are these vectors lambda I. So vertices are the points which all the points which has at two places 1 and the either n minus 2 places 0. And this hypersimplex is delta n2 is given on this way, and it belongs, because of the way it's defined, since it's the image of the moment map, belongs to this hyperplane, and it is of dimension n minus 2. For example, when n is equal 4, delta 4, 2 is a classical octahedron. And then using these Pluker coordinates on a Grassmann manifold, we defined the, as I said, we need some additional structure in order to construct a model. We defined the stratification of Grassmann manifolds. The stratification can be defined in a much more general way, but for the presentation, it's now easier to use Pluker coordinates. So when we consider sigma, any subset of a two element sets of from 1 to n, so sigma is here, and we consider W sigma are the points from Gn2 whose only Pluker coordinates, non-zero Pluker coordinates, are determined by sigma. So point L belongs to Gn2 if and only if the Pluker coordinates indexed by I, where I from sigma is non-zero. If this set is non-empty, then we say it is a stratum. And such set sigma, for which W sigma is a stratum, we call an admissible set. And then we proved that any stratum is invariant under the action of the algebraic torus, that the strata are disjoint for different sigma, for sigma 1 and sigma 2. W sigma 1 does not intersect W and sigma 2, and the union of all strata is Grassmann manifold Gn2. So in this way we define the stratification of the Grassmann manifold. This is not new. This is known thing. And then what we proved is that we have a moment map and we have a stratum. And when we apply moment, the image of the stratum by the moment map is a relative interior of the polytope P sigma, where P sigma is a convex hull of those vertices of the hypersimplex delta n2, which are indexed by sigma. So W sigma is defined by the points from delta from Gn2 whose non-zero Pluker coordinates are indexed by sigma, and this stratum maps to the interior of the polytope, which is convex hull of the vertices of the hypersimplex delta n2, which are indexed by sigma as well. And we proved that all points from a stratum have the same stabilizer. So we get the torus, quotient torus, which acts freely on W sigma. And such P sigma is a polytope, some subpolytope delta n2. And for such P sigma, we say to be admissible polytope. These admissible polytopes, the situation is much more complicated than a case of quasi-toric manifolds. C star to the n, yes. Yes.
And one more question concerning terminology and algebraic manifold. This is a smooth algebraic variety?
No, this is not smooth, not necessarily smooth. Yes, not necessarily. We could. So and just I want to then what we proved when we map W sigma to when we consider this moment map Okay, we proved this theorem that that orbit space W sigma by the action of this algebraic torus, which acts freely on W sigma, is an algebraic manifold, and it holds that the orbit space by the compact torus is homeomorphic to this product. How we prove that? We actually consider the moment map from the orbit space of W sigma by compact torus to the polytope S sigma 0, and we prove that this is a fibration with the fiber F sigma. So it means that it holds that the orbit space homeomorphic to this product. This is we proved in our early paper, I think 2019. And then among all strata, we have a main stratum. Main stratum is given by those points from Grassmann manifolds whose all Puker coordinates are non-zero. And this main stratum is easy to see. It's an open dense set in GN2. And according to what we proved, the orbit space of this main stratum, Tn-1 here acts freely, is homeomorphic to the interior of the hypersimplex time Fn. For Fn, we actually deduce Fn is the orbit space of the main stratum by the action of the algebraic torus. And actually, we prove that Fn is given in this way. It sits in CP1A on the power n, where CP1A we get when we remove from CP1 these 3 points, and n is these binomial coefficients, and it is given as an intersection of these cubic equations. And from this one can see actually that our since we can, from this cubic equation, we can eliminate a lot of coordinates, and we can see that our space Fn is actually MON. So we have here actually n-3 free coordinates. M0n, the space of n-point in the curves of genus 0. And then now we want, in developing this theory, we want to describe. We have a stratification, we have defined stratification, we have admissible polytopes, we have these F sigma spaces of parameters, and we want somehow to develop a little bit further and to describe these admissible polytopes. First, we proved if we have admissible polytop which sits inside the hypersimplex delta n2, it can be either of dimension n-1 or n-2. N-1 is a maximal dimension because hypersimplex delta n2 is of dimension n-1. So it can be either of the maximal dimension or 1 dimension less. But what is nice here that these admissible polytopes, which we actually defined as the images of the strata by the moment map, can be defined using a nice hyperplane arrangement. So we consider this hyperplane arrangement, which is given by this plane. Some xi is equal to 1, where I goes to some subset S from the 1 to n of p elements, and plus these hyperplanes xi is equal to 1 and xi equals 0. These hyperplanes xi equal to 1 and xi equal to 0 are actually, they contain the facets of our hypersimplex delta n2. And then we consider this hyperplane arrangement, and by LA, we denote the corresponding lattice of this hyperplane arrangement, so all possible intersection. And then we intersect this lattice with the hypersimplex delta n2. So we in this way, we obtain some decomposition of the hypersimplex delta n2 induced by this lattice LA. So we call it chamber decomposition of delta n2, which is induced by this lattice. What we prove that these admissible polytopes of dimension n-1 and n-2, which sits inside delta n2, can be described using this hyperplane arrangement. So any admissible polytope of dimension n-2 can be obtained as intersection of this hyperplane with the hypersimplex delta n2. So admissible polytopes of n-2 we obtain if we intersect hypersimplex with these hyperplanes. Admissible polytopes of dimension n-1, it's a little bit complicated. We consider half spaces which are determined by this hyperplane from our arrangement, and then consider all admissible collection of these half spaces, we say that some collection is admissible if two HS1 and HS2 belong to that collection, that S1 and S2 do not intersect. So we consider all some hyperplanes whose indices do not intersect, and consider half spaces defined by these hyperplanes, consider the intersection and intersection of delta n2, and in this way we get admissible polytope of dimension n-1. Okay, but now we have admissible polytopes, and we have admissible polytopes define as well chamber decomposition of the hypersimplex delta n2. What is the chamber? We consider all possible intersection of admissible polytopes. So chamber C omega we obtain as intersection of admissible polytopes, some admissible polytopes such that C omega does not intersect any other admissible polytope. So we may have a lot of polytopes inside delta n2. These polytopes intersect and they form the chamber decomposition of delta n2. And what we proved that the chambers defined by these polytopes coincide with the chambers defined by the lattice of this hyperplane arrangement. Okay, then further, as I said, we have a moment map Gn2 to delta n2. This moment map is Tn invariant, so it induces the moment map from the orbit space to delta n2. And then we can consider the pre-image of any chamber C omega hat. We proved that the same hold for as for admissible polytope. So when we consider the C omega hat, which is pre-image of the chamber in the orbit space, it is homeomorphic to C omega times F omega, where F omega is topological space, which is a formal union of spaces of parameters of a strata formal union of spaces of parameters for the strata F sigma such that sigma belongs to omega. We know that the space of parameters of main stratum always belongs to F omega, since any chamber C omega belongs to delta n2. F omega is a compact space, it is compactification of Fn. So we have a hypersimplex delta n2. We have its decomposition into chambers. We have the orbit space over this hypersimplex. And when we consider the pre-image of any chamber in this orbit space, it is homeomorphic to this chamber C omega and some compact space, which is compactification of the space of parameters of the main stratum. And now, what was our goal? So we have the main stratum, which I already said, it's homeomorphic to this product. The main stratum is then set in Gn2, so its orbit space is then set in orbit space of the Grassmann Gn2. So the closure, the closure of this orbit space of the main stratum is Gn2. On the other hand, we have a stratification of Gn2, so we have a stratification of this orbit space, and this piece is homeomorphic to this product. And what was our problem? We wanted to find the model from this orbit space starting from this. And what was our goal? To find the compactification Fn for the space Fn. We call it universal space of parameters such that there exists a projection from this product, because we have the orbit space of the Grassmann manifold is this product, delta n2 interior times Fn. And we want to find the model for our orbit space of the similar form. So the form delta n2 times Fn, and that we have this projection that the pre-image of the orbit space of each stratum is similar to the orbit space of a stratum itself. So the orbit space of the stratum itself is a P sigma 0 times F sigma, and we would like the pre-image in this product to be P sigma 0 times F sigma tilde. For some F sigma tilde is Fn. F sigma tilde is we call universal space of parameters, and that there exists projection from this space F sigma tilde in Fn to our space F sigma, such that this projection Pn, which goes from this product to this orbit space, and H sigma is trivialization, coincides actually with the projection from F sigma tilde to F sigma. So we wanted our orbit space locally is modeled by the product P sigma 0 times F sigma, we wanted to find the model for the whole orbit space of the form delta n2 times Fn, which is locally again to be modeled by F P sigma 0 times F sigma tilde. First, we noted we needed compactification of our space of parameters Fn of the main stratum. We first noted the first step is the comp Fn belongs to CP1A on the power n. The first compactification is Fn bar. It's compactification of this space in Fn bar in CP1n. It's just a smooth algebraic variety given by these cubic equations. And we noticed that this compactification cannot serve as Fn, cannot serve as this compactification does not satisfy the condition that it can serve to construct the somehow global model for our orbit space. And because of that, we applied techniques from algebraic geometry called the wonderful compactification. Actually, we started from this compact space Fn bar and applied the method of wonderful compactification to obtain the new compactification from Fn, which is going to satisfy our requirements. So I'm just, this is the wonderful compactification. Actually, very roughly speaking, we may start with some compact manifold, and we have some smooth variety. We have some sub-varieties which are not good for our purposes, and actually we blow up this variety along these sub-varieties and obtain the new compact space, which is compactification of the initial one, but it's going to serve for our purposes. So actually, we saw that these FA hat given on this way are sub-varieties for which sub-varieties is Fn1 bar, along which our requirements are not going to be satisfied. And using wonderful compactification, we take this Fi hat, their intersection, as the building set, and actually we do iterated blow-ups along this building set, starting from this set Fn bar, and the result, using theory of wonderful compactification, we obtained the smooth compact manifold Fn, and for them, we prove for this space, we prove that it's going to satisfy all our requirement to be universal space of parameters. Just to say how it works, say when we have Fi bar, it's CP1 cube given by this equation, and then the building set actually is this point. We blow up Fi bar at this point, and our universal space of parameters, which are going to serve for our purposes, is F5. It's actually del Pezzo surface of degree 5. Or say when n is equal to 6, our F6 bar is given by these 4 equations, and we see that the building set consists of this point and these 4 sub-varieties, and our universal space of parameters using the wonderful compactification, it's these iterated blow-ups where these are strict transforms. Okay, and now I just want to say about virtual spaces of parameters. I said virtual spaces of parameters are the pre-images of the orbit space of a stratum in this product delta n2 times Fn. The virtual space of parameters, when we describe this compactification Fn as the blow up, it's a union. Its union is the space Fn. The virtual space of parameters for the main stratum coincide with the spaces of parameters, and actually our requirements prove that there exists a projection from F sigma tilde to F sigma for any sigma. And as I said in the beginning, a point L from Grassmann, orbit space of Grassmann is said to be singular if its corresponding virtual spaces of parameters and spaces of parameters are not homeomorphic. So spaces of parameters are real spaces as orbit spaces, and virtual spaces of parameters are actually pre-images of the orbit space in this product delta n2 times Fn. And what is nice, we prove that when we fix one chamber C omega inside delta n2, and when we consider all virtual spaces of parameters F sigma tilde, where sigma is in omega, so we consider one chamber C omega. C omega is obtained as intersection of some admissible polytopes F P sigma. We obtain F sigma tilde. We consider F sigma tilde, which corresponds to this sigma. then the union is going to give Fn, and this union is disjoint. So over any C omega, when you consider Fn, the corresponding virtual space of parameters are disjoint, and the union Fn. So what does it mean? It means that we can define the projection from Fn, universal space of parameters, to F omega by following way. We take Y from Fn, then using the union above, it exists unique F sigma tilde, such Y belongs to F sigma tilde, but then from F sigma tilde to F sigma, there exists a projection, and F sigma is a subset of F omega. So this is very somehow important fact. Up to now, I was talking about interior of delta n2. What about the boundary? Sits about boundary delta n2. The boundary of delta n2 consists of n copies of hypersimplices delta n minus 2 and n copies of simplices. So the pre-image in the orbit space of the boundary is n copies of the orbit spaces of Grassmannian Gn minus 1, 2, and n copies of projective space. When we consider the universal space of parameters of these spaces, the universal space of parameters, the parameters CP1 there are no parameters are the points. And here the universal space of parameters is Fn minus 1 in the same way. What we proved is that this Fn minus q, which is universal space of parameters of the Grassmann that sits above the hypersimplex on the boundary of delta n2, is actually the image of the projection. There is this projection from Fn to Fn minus 1, such that we Fn minus q, we can obtain as the image of this projection, but just forgetting the qt coordinate. So when we consider Fn and project just forget the coordinate indexed by q, then we get Fn minus 1. And in this way, we obtain that our projection from Fn to F omega is defined for any chamber C omega. For chamber C omega sitting inside delta n2, I already defined it. For the chamber which sits on the boundary of delta n2, I first project Fn to Fn minus 1 q, and then inductively I have projection to Fn minus 1 q to F omega for that chamber C omega. So altogether, I describe everything. Altogether, we have the space un delta n2 times Fn. Then we define the projection G from un to the orbit space, which is given as the union of this C omega hat, and the following way. I take x and y. When I take y from Fn, then I take x from delta n2, there exists unique chamber C omega, such that x belongs to C omega. Then I consider for this C omega, I consider P omega y, where P omega maps from Fn to F omega. Then I get pair x P omega y, x is C omega, P omega y is F omega, and by H omega, I go to C omega hat, which is in the orbit space Gn2 by Tn. And we prove that this map is continuous and that it resolves the singularities of this orbit space. So what are the ingredients of for the construction of our model? It's universal space of parameters, spaces of parameters of the strata and over chambers, virtual spaces of parameters, projections from the virtual to real space of parameters, and projections from the universal space of parameters to F omega, and the projection from Fn to Fn minus q. We actually show that all our ingredients give the can be that Hassett model, that objective morphism of Hassett model HON can be realized in terms of these objects. I go back now to this Hassett category. As I said, the objects are the spaces M bar 0A, the weighted curves of genus 0 with A weights, and the morphism are reduction and forgetting morphisms. What are this is the theorem formulated by Hassett, how we prove the existence of these reduction and forgetting morphism. He said when we have two weights, A and B, such that BI is less equal AI for any I, he said that there is birational reduction morphisms, and he described how it works. He takes any curve and then collapsing components of the curve along which this fails to be n2. This is proved by Hassett. existence of reduction morphism, and also he proved the existence of forgetting morphism when we have some collection of weights and we have some subset of these weights such that these conditions are satisfied, so it should be satisfied. Then he said that there exists natural forgetting morphism. Natural morphism for this space to this space, again, obtained by successfully collapsing components along curve, which this divisor fails to be ample. And then Hassett also described in his paper boundary divisors for the Dix reduction morphism. He actually proved that the boundary divisors are of the following form. So this is theorem proved by Hassett, and then that the reduction morphisms on the boundary divisor, it's just a contraction. It contracts this component 0 AI prime and factorizes on the following way. So it contracts 0 1 prime to 0 1 A1 prime to mg ag prime, and then just consider the reduction morphism from the reduction morphism from ag prime to bg prime. Then he considered the domain of admissible data in case when genus equal to 0. This is the domain of admissible data, DON, in a case when G equal to 0, weighted data. And then he considered the decomposition of this domain, the chamber decomposition of the domains D0N by these hyperplanes. I mean, these are the similar hyperplane which actually we realized, which we used to description of our hyperplane arrangement to define admissible polytopes. And consider the chamber decomposition of delta 0n using the hyperplane arrangement, and he proved that when we take one chamber from this chamber decomposition, and that this moduli space does not depend on the chamber. So the moduli space is a constant on any chamber on this chamber decomposition on weight data. And then he introduced the boundary of these admissible data. By the boundary are going, or Qn is the same, the boundary are going to consist of those points whose sum is equal to 2. We noticed immediately that his boundary is just interior of our hypersimplex delta n2. And then he noticed that one can employ here the geometric invariant theory and consider CP1n with diagonal action of the group PGL2, and consider factor linearization of this action given by the condition that the sum is equal to 2. And then it's known that linearization is typical when the sum of any for any subset, the sum is not 1, and otherwise is atypical. And then he considered the geometric invariant theory quotients of CP1 by this linearization. And he proved that when we take L from the boundary of delta 0n, if it is a typical linearization, then it's in boundary of delta d1, then there exists a neighborhood U of such L, such that the intersection of U with a domain of admissible weights is contained in the open chamber of the 0n, and for each weight data in this open chamber, the weighted moduli space is isomorphic to the geometric invariant theory quotient. But it is typical linearization. When linearization is not typical, he also proved that there exists such neighborhood, but there is not isomorphism. There is birational morphism between these objects. When we take some linearization T1 Tn on the boundary, then in the neighborhood of this linearization, this neighborhood is contained in some chamber, and actually moduli space weighted moduli space over this chamber, as well as geometric invariant theory quotient, does not depend on any weight chosen from this chamber. And for T1, Tn, linearization from the boundary of delta n, we denote by AL the corresponding weight data. And now go back to our construction. F sigma, as I said already, Fn is homeomorphic. It's actually isomorphic to MON. So the moduli space of genus 0 curves with endpoints. For any, we can very easily deduce from our work that when we take spaces of parameters F sigma of any stratum, it is going to be homeomorphic to MOM for some n between 3 and n-1. So the spaces of parameters of any stratum can be seen as the moduli spaces of n-pointed curves of genus 0. Then one can combine the results of David Manford and versus Kirwan. He proved that, but completely different approaches. One can see from their results. Then when we consider chamber C omega, and we consider the union of all strata F sigma, which are indexed by W sigma, which are indexed by omega, then the space of parameters of the space of parameters F omega of the chamber C omega, which we introduced, is actually homeomorphic to the categorical quotient or the action of C star n on this space. Then Kirwan proved that this categorical quotient described here actually coincides with the geometric invariant theory quotient of CP1 given by this linearization for arbitrary T1 Tn is C omega. As a result, we obtain that our space of parameters F omega over chambers we introduced, it coincides with the geometric invariant theory quotient GL, where L is a linearization given by any tuple from C omega. And we prove what's further. So spaces F sigma we realized as a moduli space, spaces F omega we realized as a moduli space. Our universal space of parameters Fn, which constructed by the method of wonderful compactification in our recent work, we prove that it is diffeomorphic to the space M bar OA. It's M bar 0n, which is the Lin-Mumford compactification, where A is equal 1, 1, 1. For the virtual spaces of parameters, we can prove it this all topologically using the local coordinates and everything right down in local coordinates. For the virtual spaces of parameters, we prove to have this formula. Any virtual space of parameters is homeomorphic Fp bar, where Fp bar belongs to Cp1 on P times Fl, or on the following ways. And the projection is given by the projection to Fi. And then further, our space Fn bar, we started with in the space of wonderful compactification. We can see from the Hassett examples and description that it is isomorphic to the weighted moduli space of weighted curves M bar 0 an. And so for the virtual spaces of parameters, according to the previous remark, we obtained that the virtual spaces of parameters can be realized as the moduli spaces of stable weighted curves. So the compactification of virtual spaces of parameters is given on this form. So using geometric invariant theory quotient, we obtain F omega is F omega is homeomorphic to geometric invariant theory quotient of the given by the linearization T1 Tn, and this is further homeomorphic to the weighted to this space M bar 0 a T1 Tn for an arbitrary T1 Tn is C omega. this is when dimension is C omega is n-1. So it means then in this case, this linearization using geometric invariant theory is typical. When dimension C omega is n-2, so the sum of these coordinates is equal to 1, so the linearization is not typical. So we can say that there is birational morphism from this space to our space F omega. Further, Hasse described the boundary divisors. The analog theorem, our theorem, is that the maximal dimensional submanifold consisting of singular points from our projection is given in the following way. So it follows that our projection P omega from Fn to F omega, so Fn is just is this space, it is m bar 0a11. F omega is this space T1 Tn, which is linearization, and it is given on the divisor by the following. We just proved that completely analog to Hassett reduction morphism, to Hassett forgetting morphism on the boundary divisors, analogs that they can be realized by our map, by our projection P omega and our projection by our projection P omega, which are described absolutely in terms of in topological terms. So what I say, so we have the projection for when we consider P omega Fn to F omega, when the dimension of C omega is n-1, then our map P omega from Fn to F omega coincides with the reduction morphism given by Hassett. Reduction morphism given by Hassett. When dimension of C omega is n-1, because we do not have an isomorphism between F omega and geometric invariant theory quotient, our projection P omega coincides with the Hassett reduction up to this map rho. And our projection RQ from Fn-1Q, which was ingredient in our model for the orbit space, coincides with the forgetting map given by Hassett. So all notions which we introduce for constructing the model for our orbit space can be described in terms of moduli spaces of weighted stable curves. Morphisms, the continuous map which contribute in description of our model can be described in terms of reduction and forgetting morphisms in a Hassett category. So actually we have a correspondence with the Hassett category H01 and our model for the orbit space. Just 1 minute why one can ask very simple question. Okay, we have established this and why it's important, but our goal was to describe the topology of the orbit space Gn2 by Tn, and very complicated task is to describe the homology. On the other side, when we consider the moduli spaces, exceptionally for genus 0 curves, we have described the Chow ring, we have described additively the homology given by results of old paper by Sean Keel. So we can translate all these results to our cases, to our construction, and to explicitly describe the homology of our orbit spaces, or at least to provide the complete explicit method for the description of their homology. Thank you very much.
Thank you, Svetlana. Please, questions, comments?
As I remember, you said that at some point that your universal parameter space is diffeomorphic to the Deligne-Mulford compactification, right?
Yes, MON bar.
Is it just a diffeomorphism, not an isomorphism of algebraic varieties?
We prove that is diffeomorphism.
So you don't know, or it is not true?
We don't know. We actually, because we did not need that.
There is some hope that this could be true.
because actually when we proved that, we used our description of the universal space of parameters using wonderful compactification, and description of M bar O(n), the Lin-Manford, using Keel's approach as iterated blow-ups of. They were described by Kapranov, Keel. There are different approaches. We use this one to establish the diffeomorphism, but actually we did not concern that question. To say.
Thank you.
Sveta, thank you very much. I'm happy for you. But certainly, I should like add a few words. In September this year, there was 110 years for Israel Moiseyevich Gelfand. Sveta introduced the result, which very close to some ideas for the topics which was the central interest of Israel Moiseyevich Gelfand. He wrote few very seminal paper related with the topology Grassmann manifolds, well-known papers Gelfand-Serganova, Gelfand-Macpherson, Goreski, and so on. And I will be happy to introduce Israel Moiseyevich with such kind of result, but I should like to mention a few comments what exactly what Dima mentioned. 20 years ago, where Gelfand was 90 years, the Kapranov published very seminal paper where he described what Mumford compactification was now as Chow factor of Grassmann manifold. Exactly at that time, we with Taras start to construct toric topology and obtain many results of the structure toric varieties, toric manifolds. And the right idea, Grassmann manifolds, of course, it is not toric variety, but inside we have a lot of toric varieties. And my idea was, can we apply the method of toric topology to understand better the structure of toric manifolds? It was my suggestion, and I invite Svetlana work together for such problem. Extend the method of toric topology to the case of Grassmann first. Second, of course, we can discuss G and K, K-dimensional complex subspace in Cn. But when K is 1, it is CP1. From algebra, it is toric manifold, smooth, and from topology, it is very simple. But there are very important example, Gelfand-Serganova, which show that case K is 2, it is a very special case. If we go to the, for example, genus 7 example, you obtain a very complicated, much more complicated. So a nice idea, maybe the case exactly K is 2 gen 2, it is a case where we can obtain deep result related with many problems of mathematics. Our first result with Svetlana was N is 4, G 4, 2. Result was exciting. We show that orbit space homeomorphic to S5. I immediately call to my friend Winberg and ask Eric, unbelievable, why? Did you know this result? He, of course, mentioned it, you know, that there are one of his people, Stirt, who work in this case. But it turns out it became new. But case N-5 show to us topological space, which much more complicated. And let me inform young student that problem described topology of Grassmann GN2 up to 10 up to very seminal and problem, which will be interesting. It is certainly, from topological point of view, very important, very interesting spaces. But as you can see from the talk of Svetlana, it is not any topological space. It is a space which we can consider as a bridge between algebraic topology, algebraic geometry, combinatorics, because hypersimplics is one of the best convex hole. And so I can mention. So what I invite young people thinking about algebraic topology of such interesting topological space, Grassmann N2 up to action compact torus Tn. Thank you.
Unfortunately, we have no time for further discussions. I propose to make a 5-minute break